Esse aí é suficiente, prof? Eu quero que coloque alguma coisa das publicações.
Eu acho que sim, cara, uma coisa bem...
Acho que vai começar. Boa noite a todos e todas. Bem-vindos a mais um colóquio de pós-graduação da Escola de Enfermagem da Universidade de São Paulo. Meu nome é Adriane Canicoba e, juntamente comigo, nessa comissão organizadora dos colóquios, estão a Camila Mendes, Raíssa Otis e Camila Iga, todas nós discentes do programa de pós-graduação da Escola de Enfermagem da USP. E hoje é com muita alegria e honra que nós recebemos o professor Dr. Kevin Wu, que ministrará o colóquio Expandindo, toolkit for Statistical Analyses, e o professor Kevin é da Queen's University, no Canadá. Nós destacamos que a lista de presença será disponibilizada via chat aqui no YouTube, logo após a apresentação do Dr. Kevin, e o certificado de participação no colóquio vai ser enviado via e-mail posteriormente. Nós convidamos vocês a seguirem todas as nossas redes sociais, no Facebook e Instagram, para receber as informações sobre os próximos colóquios que vamos desenvolvendo ao longo do ano e no próximo ano, e se inscrever aqui no nosso canal do YouTube e ativar o sininho para receber as notificações. Dr. Kevin, once again, thank you for being with us tonight. It is a pleasure for us, and thank you for your time. Professora Vera, pode ficar à vontade.
Obrigada, Adriane. Boa tarde, good afternoon, good evening. Thank you very much, Professor Kevin Wu, for being with us again and conducting this lecture, this not just an open lecture, but also we did a partnership with this group of students in colloquios da pós-graduação. So thank you very much. It's a pleasure to introduce Professor Kevin Wu. As Adriane said, Professor Kevin Wu is Associate Professor at Queen's University, School of Nursing, the School of Rehabilitation in Kingston, Canada. His clinical and research interests focus on chronic disease management, gerontology, wound healing, knowledge translation, and patient safety, using a variety of research methods and large administrative databases. Nowadays, he's a visiting professor at the School of Nursing of the University of São Paulo in our graduation program, PROESA, and collaborating with our research group, GPET, and supported by CAPS Print at this moment. Thank you very much, Professor Kevin. Please feel free to start your lecture.
Thank you so much, Professor Vera. I'm just going to show my screen, and I'm right here. So it's a pleasure to be invited to participate in a lot of activities here in Brazil, and it's such an honor to be a visiting professor at the University of Sao Paulo. So as Professor Vera mentioned, I'm a professor at Queen's University. And I do teach statistics in the last about 8 years at the master's program. So today I'm going to talk to you about expanding your statistics toolkit. So I assume a lot of you will have some basic knowledge and background in statistics already. So the discussion today is really a little bit refresher to review some of the basic concepts behind statistics, and also to expand on some of the examples that I'll be using, some of the more advanced or some of the less used technique for analyzing data as well. So I think to start talking about statistics, I think we need to describe there's actually two big groups of statistical analyses techniques. One is called the descriptive statistics that will allow us to describe the data. And we'll come back to talk more about different ways to describe the data. And then the other type of statistics, we call that inferential statistics. The purpose of that type of statistics is to test hypotheses. We hypothesize that when the weather is hot, there are more people going to go swimming. So that's the hypothesis about the relationship. And that's why we have to do a survey. We have to do a evaluation. We have to do a formal study to determine whether the hypothesis is true or not. So, and we rely on statistics to confirm or validate, to prove if the hypothesis is valid. So let's start with the discussion about descriptive statistics here. So the main thing that when you think about describing, the purpose of descriptive statistics is to describe the data. There are different ways of describing, summarizing, if you may, the data. So first of all, we can describe the central tendency of the data. So there are different ways to measure central tendency. We can report the mean, the median, the mode, or the quartiles. In epidemiology, epidemiologists, they love to report quartiles because in a lot of the phenomenon, you may have a lot of outliers. So by describing the interquartiles, basically is the center cluster of the data, then you eliminate a lot of outliers in your description, in describing, in your descriptive statistics. So the most common, of course, is the mean. That we'll come back to have some more discussion about that. And the other concept, as you can see on your right-hand side, is the measurement of dispersion. And basically describing how the data is being spread out across a continuum of potential scores. So you can measure standard deviation, you can measure variance, and you can measure range. So the basic concept, the most common, the most easy concept that we all associate with when we talk about describing the data in statistics is calculating the mean. For example, how old are you? And so in order to calculate, let's say if we want to summarize the age of the participants in this seminar tonight. So what we might want to do is to collect all the information from each of you. And then what we can do is to add them up. So let's say we have 5 people respond to a survey. So the age, very young people, 21, 22, 22, 23, 24. Those are 5 people. We add them up, divided by 5. So your mean age is 22.4. So we can say the mean age for the respondents representing this group of people participating in tonight's seminar is about 22.4 years old. The important part about statistics is, are you confident that this is the true finding? 22 is the mean age. If you repeat this survey, this study again, are you going to get exactly the same answer, 22.4? Is it going to be higher or is it going to be lower? In other words, is your finding 22.4 years going to be generalizable to the general population? And that's why we often do along with the estimation of the mean score, or mean age in this case, we also report something called the 95% confidence interval. So as you can see on this slide, hopefully you can see my cursor as well. What we're trying to do is describe the range where the 95% of the score is going to be defined within this curve. So the mu is in the center that represents the population mean. So in other words, the easy way for me to explain what 95% confidence interval is, if you repeat the same study 100 times, 95% of times, the score should be between A and B, right? So let's say the mean score today, based on the data that we have collected, was 22.4. I'm going to repeat the same study, collecting 5 people 100 times. So you may have another mean that is 55, and a mean that is 18, and a mean that is 45. And then at the end, so you plot out all the mean scores, all the mean ages 100 times. You should be able to plot the score on a curve. So the 95% of the scores, let's say, would be between 18 and 65. That's the hypothetical situation. So that gives you the confidence, give you some idea how spread out the number is. Because if you report to me that your mean age score is 22.4 and the 95% confidence interval is 15 to 65, that's a very big confidence interval. And then your mean age that you're reporting in your study, 22.4 years, may not be a very, very generalizable number because you've got a very big range of confidence interval. So just to illustrate an example, this is a recent study that we published this year. We look at a lot of studies that evaluated the use of topical cadhesymer iodine for the treatment of chronic wounds. So we looked at 436 publications that fit the criteria, how the topical cadhesymer iodine can improve wound healing, whether it is improving X-ray level, reducing the slough, addressing the burden of infection. So 13 of those, 13 of the 436 publications fit the criteria. So we looked at all those studies. And then we calculate the numbers. We're able to report that people who were treated with the cadhesymer iodine, on average, achieve a mean area reduction. The amount of area that is getting smaller after 8 weeks of treatment, the mean difference between the two groups, between the cadhesymer iodine group and the standard of care group, was 2.35 centimeters squared. So meaning that people treated with iodine can achieve more closure by about 2.35 centimeters squared on average after 8 weeks compared to standard of care. So yes, we reported the mean difference, the mean reduction, 2.35. At the same time, we calculated the 95% confidence interval. So you can see if we repeat the study, the same evaluation 100 times, so 95% of the time, the mean difference would be somewhere between 0.35 centimeters square to 4.36 centimeters square. So 2.35 centimeters square is right in the middle. So by looking at this confidence interval, it looks pretty good. It's a very tight interval. And that will give me some confidence that the 2.35 is actually a generalizable number that represents the true mean reduction after 8 weeks of treatment. And that's why you see the p-value is actually quite good. P equals 0.0219. And so I think I encourage people, every time you're reporting your mean values, always think about reporting 95% confidence interval, because that will give people some idea how confident it is that we can trust the mean score that you're reporting in your study. So we can also describe the data graphically. So one of the most common way of describing is, there are many different types of graphs, histograms, bar graph, scatter plot, and so on and so forth. So this is one of the example of a bar graph describing if you're collecting data to ask people to choose their favorite colors. It could be blue, it could be red, it could be yellow, it could be purple. So then you're describing the different preferences. So what we want to see, you might ask, why do we need to worry about graphs? I got numbers, I got statistics, I don't want graphs. Well, in fact, doing a graph is very, very important, because what you want to see at the very beginning, even before you do any statistical tests, is to determine if the data is normally distributed, what we call a bell curve distribution or Gaussian distribution. Because if the data is not normal, a lot of the tests you have to use may not fit into the assumption. So you have to use a different types of tests to evaluate your data and test your hypothesis. And in most cases, if you have very big sample size, and usually the data should follow this normal curve. So for example, if we plot everybody's wound healing, how the wound behave over time, and they will follow inflammation, proliferation, remodeling, and how long does it take to go through inflammation? On average, it's like this, from 0.0 to about 10. And that's the distribution. Yes, some people may heal fast, may go through inflammation faster. Some people may have longer inflammation. But usually, if you collect enough data, all the information should follow this normal curve. As you can see, inflammation, proliferation, and remodeling. And depends on the type of sample and depends on the type of patients, depends on your research question. We don't always have a normal symmetrical curve like this, the normal curve. And sometimes the data may be skewed, and in this case, it is skewed to the left. And so you can see that the more scores around the right-hand side. So that's why it's skewed to the left with the tail pointing towards the left. Versus, you could also have data that is skewed to the right. So if you think about a good example, what kind of situation would have data that's skewed to the left with all the major scores, majority of the scores cluster around the high end? Imagine this is a visual analog scale data, and we're asking people to rate the level of pain after surgery. So I would bet any money that most people would rate the pain high. And that's why you may see the curve, the distribution for post-op patients would be skewed towards left, with most people rating the pain pretty high. Or if you have another study, let's say, what's the likelihood that people are going to try jumping off the cliff to experience it? And I would say most people may not be so inclined to do so. So again, you may see the data was skewed to one side. So why do we need to worry about this? Because when the data is skewed, then you may not be able to use what we call the parametric test to evaluate your data. So there are two ways of handling the problem. One is you can use what we call non-parametric tests, and I'll sort of mention a few of them a little later. Or you can transform the data, what we call log transformation, to normalize the data so the curve can be sort of moved a little bit to make it look more like a normal curve. The other important part about looking at the data is to looking at the shape, because a lot of situations that we may see the distribution of scores assume a bimodal pattern, meaning there are two peaks, or multimodal with multiple peaks. So in other words, the data may not be so uniform. It may represent two different type of samples. Very good example is is a lot of the scores. For example, if we think about depression score, and you may have peaks representing one peak for male and one peak for female. So if you, let's say wound healing again, it may follow a normal curve, unimodal. But when you're evaluating some of the psychosocial phenomenon, a lot of the social determinants can affect the values, and that's why you see peak values because of whether it is because of the gender differences or the income differences or some other ethnicity differences. So hopefully that's making some sense to you in terms of the importance of looking at the central tendency, how we the need to describe the mean, and also the way to describe the to report the 95% confidence interval. And at the very beginning of your data analyses, you should always plot the graph to determine whether the data is normally distributed, or do you need to separate the sample into different clusters, or log transform it, or use some other type of statistics for the analyses. So the other concept is the variability. As I mentioned before, it's really a measurement or description of the spread of your data. So a very important concept that that a lot of the parametric tests that we use for normal distribution is what we call homogeneity of variance. So I think this is a nice curve to show you that, let's say, all those little dots, the different data points, and they're all spread evenly across the line. And so that is an important concept, because you don't want to have data that very close at one end and very spread out the other end. So meaning that they're not very homogeneous. And the other term that we sometimes use is the heteroscedasticity versus, and you can see that all the red dots are very, very close together, and meaning the variance is very, very minimum and very uniform as well. So that's the term that we use to describe the homogeneity of variance. We call that homoscedasticity. So again, just a refresher for you to describe how how each data point can deviate from the mean. We minus one from the other, and what we can do is to square and divide by the degree of freedom. Usually is n minus 1, the total sample size minus 1. And then at the same time, what you can do is take the square root of the number, and then you can arrive at the standard deviation. So this is a good unit to describe the variability of the data, the spread, and the dispersion of the data. So if you have a score and with a very, very high standard deviation, so similar to the explanation I gave you earlier about the 95% confidence interval, if you have a very large standard deviation, then it's not so confident, then the reader may not be so confident that whatever value that you're reporting is representing the population, because you got a wide range, right? So it's like, what is the age of this group? Is range from 0 to 100. Of course, I mean, it's useless to say that this is the potential range. But if I tell you the age for this group is range between 20 to 25, so much narrower, then it gives me more confidence that whatever you're reporting, that you mean 22.4 is actually trustworthy. So the other thing, what we can do with why we calculate the standard deviation is the advantage of converting your scores into a standard score as well. I was talking to Carol earlier about her study, and that's why I thought that maybe I'll just use a few moments to discuss about standard score. The other term we sometimes use is to create or to estimate the Z-score. And there are two advantages of calculating standard score, because it will allow us to determine the probability of the score that you have and how much it is deviating from the mean. And also, it can help us to compare two different scores from two different normal distributions. And hopefully, I'll give you some example, and it will be more clear to you. So remember, when we think about normal curve, there's a very important characteristics is the fact that we call it Central Theorem, and the mean is right in the middle and is represented, and we assume that center point is a 0. So that is your mean. And then your unit on the bottom here is, the unit is standard deviation unit. So you have 1 standard deviation away from the mean, 2 standard deviation away from the mean, and 3 standard deviation away from the mean to describe this normal curve. What's interesting about normal curve, the assumption we can make is 1 deviation above and below the mean would cover 68% of all the data if the data is normally distributed. And if the and for the area 2 standard deviation above and 2 standard deviation below the mean, that will cover 95% confidence, 95% of the data. And that's why when we think about the 95% confidence interval, so that's the that's the traditional range that we use. And then for the 3 standard deviation, then you have the 99.7%. So most of the data would be within the 3 standard deviation above and below. So the Z-score is actually quite helpful. I'll give you an example first. So we know that pressure injury is very common in people who are critically ill. And one of the study by Cox and her group, and they look at they did a systematic review and meta-analyses. What they were trying to validate is the fact that Braden may not always capture the important variable that linked to the development of pressure injury. So they look at all the literature, identify the other variables like blood pressure, oxygen, incontinence, steroid use, the use of vasoactive substances. So as you can see that, so by converting some of those values to the standard score or the Z-score, so you can see that blood pressure is 1.96 standard deviation above. So meaning that individuals with low blood pressure are 2 times more likely to develop pressure injuries in the ICU. The same as low oxygen, 2 times, incontinent stool, 1.3 times, support surface. If they need support surface is 1.3, steroid use 1.2 times, so on and so forth. So that gives you the advantage of comparing different variables from different studies, the strength of the of how influential each variable is on the outcome variable, on the dependent variable. So in order to convert your score, your raw score, to a standard score, it's very easy to do. This is the formula. So it is the score that you have minus the mean divided by the variance, by the standard deviation rather. So that's a very easy to do calculation. So let's go back to the examples that we saw earlier. So we can convert the age scores. So age minus 22.4 divided by the standard deviation, which we calculated before, was 1.14. So in other words, so if I have someone that is age 24, what is the standard score for that individual? So that will be if you have 24, if you go back to slide, so 24 minus 22.4 divided by 1.14. So in other words, this individual is 1.4 standard deviation above the mean with 22.4. So that's helpful for us to really gauge the higher the number, of course, the more likely that you're deviating from the mean, right? So the other way of using the standard score is allow you to do some comparison between different tools and different population, different studies. So for example, if I have a study with two different tools to evaluate depression, one is the back depression inventory, and one is called the self-rating depression scale. And the individual score was 23 from the back inventory, 68 from the depression scale. Because there are two different scales, so the score itself doesn't really make sense to me. So is 23 better than 68? Or how bad is it when you think about it? Seems like it's a big difference. But is it a big difference? Because it depends on the total score as well, right? So what we can do is convert those scores into a standard score. So if the patient score is 23, and we know the sample mean was 11.3, standard deviation was 7.7, so we can standardize it. So it'll be the mean, the 23 minus 11.3 divided by 7.7, the same as the self-rating depression scale. So in that sample, I can do exactly the same to convert this score. So 68 minus the mean value in the sample, 52.1, divided by the standard deviation of the sample, 10.5. So the Z-score for the back inventory, 23 minus 11.3 divided by 7.7 is 1.52. The self-rating depression scale is 68 minus 50.1 divided by 10.5, 1.51. So now you can see 63, a patient that scores 63 on the depression scale, the back, and the 68 on a self-rating depression scale, they're similar. So in other words, the score is not so much different whether it is on the back or the self-rating depression scale. So that's the advantage of doing the conversion to a standard score. Standard meaning you eliminate the original unit and convert everything to the same unit, and the unit is the standard deviation. So in other words, this individual that scored 23 is 1.52 standard deviation above the mean. The person who scores 68 on the self-rating depression scale is 1.51 above the standard deviation above the mean. So let's go through some of the key aspects around inferential statistics. The purpose of doing inferential statistics is to test hypotheses. And it's so important to understand the concept of hypothesis testing. So similar to the saying that we always presume someone is innocent until proven otherwise. So that's why when we do studies, we always have something called the null hypothesis versus the research hypothesis. So we always presume there's no relationship. We always presume there is no association. There's no outcome and no relationship between any measured variables. That's your null hypothesis. And our job is to, instead of going to the court to stand in front of the judge, what we do is we use statistics to prove this is wrong, that this null hypothesis is incorrect. So we can reject the null hypothesis. So in other words, the purpose of doing hypothesis testing is to reject the null hypothesis so we can prove the research hypothesis is correct. Because in research, we hypothesize there is a relationship between the two variables. or between number of variables. Because if we don't think there's a relationship, why bother to do your research, right? And that's why your research hypothesis always starts with there's a relationship, there is a link, versus the null hypothesis is saying that nope, there's nothing happening between the two variables, and your job is to prove the null hypothesis is wrong. So in order to do that, going back to this curve, if you think about, remember what I said earlier, that for the normal curve, 95% of the time, the values would be somewhere between 2 standard deviation above and below the mean, right? So this is a very common observation, meaning that if I see something is that common, I'm not going to. I think we can accept that as it is. So we accept the null hypothesis because it is a common, it is not exceptional observation, versus if the value is very rare, very unusual. And how unusual it is? Well, more than 95% or less than 95% of the time, this is happening. So meaning that it's in this green area, then because it's so rare, this is happening. So we can reject the null hypothesis to prove that this is so rare that this is not a common occurrence. It is not by chance. It is not by luck that we find this association, this relationship. This relationship has to be real because it is so rare that we're able to find this, and that's the crux, or that's the principle why we select p-value as 0.05, because or 5%, because if you have 100% minus 95%, that's 5% of the time in this green area. 5% is the same as 0.05. So in other words, if my finding, this relationship is p-value less than 0.05, it is so rare, and I can actually reject the null hypothesis. And that's the purpose of testing your hypothesis by using statistical tests. So the first one that I want to review with you is your t-test. So the purpose of doing t-tests basically is to compare the two mean values from your two different groups. And remember, the null hypothesis, basically, H0 here, H0, is that there's no difference between the two means. So unless you can prove to me that the p-value is so rare that the chances is so small, then I can reject the null hypothesis that the one mean is not the same as the other mean. So I think from a pictorial illustration, you can see that the two population, so and how big a difference does it take to prove that the occurrences are rare. So there are two different types of t-tests. So we can do independent t-test or dependent t-test. So independent t-test, we're talking about two different conditions or two totally different groups of people, versus dependent t-test, they're drawing from the same participants. So let's come back to independent first. So I think it's probably easier to give you an example. This is a recent study published in JWCN by Radcliffe and her colleague. They look at the impact of complex wounds on health-related quality of life. And they basically have about 111 participants, and they have 67 male, 44 female, and they look at number of different social economic variables, and they use the wound quality of life questionnaire. They have 17 questions to evaluate people's health-related quality of life. and they come up with a total wound score to represent the quality of life. So what they did was compare between. So first of all, if you're doing a t-test, the dependent variable, in this case, quality of life, has to be a continuous variable. Otherwise, you won't have a mean values, right? To have a mean, the score has to be continuous. So in this case, they compare the quality of life score between white people and black people. So as you can see, the standard deviation. So there were 3-point difference there, and the standard deviation for the white individuals and black individuals here as well. So, and they conclude based on the t-test, comparing the white people quality of life score versus the black quality of life score, there was no significant difference because the p-value was much higher than 0.05, as you can see in this example here. And they also compare the two different sexes, males and females participants. And again, there was no difference using an independent t-test. So in other words, when you're thinking about doing an independent t-test, there should be a categorical variable, male, female, white, black, or healthy, not healthy, with wounds, with no wounds, with diabetes, with no diabetes. And then your dependent variable should be a continuous variable. So this is a flow diagram to describe that the thought process you may want to go through to determine whether it is appropriate to do the independent t-tests. And you can actually find on SPSS tutorials the number of really good description about different statistical tests. So basically, you want to make sure that looking at the data, is the data normal? And if not normal, then you use the non-parametric test. In this case, the non-parametric version of t-test is something called the Mann-Whitney test. And then looking at the variance in the end. Remember, we talk about the because you have two groups, you want to make sure that not one group has a huge spread, huge variance, and the other group has a very, very tight spread of data or small variance. So you want to determine whether you can assume the equal variance between the two groups. So the other type of t-test is what we call the dependent or the paired t-test. The most common scenario is we can compare before and after, pre-test and post-test results, time 1 and time 2, because you're drawing on the data from the same people, same participants in this case. So this is another study by Parker and Finlayson, and I think it's an Australian study. They look at by introducing wound care nurses or wound champions and how they can improve leg and foot ulcer care in the primary care setting. And so what they did was they look at this model and try to educate the primary health care people in Australia. They did a pre-test and post-test type evaluation. So meaning they look at the type of care before, and by introducing the wound care nurses or the champions, they do an evaluation again. So there were about 109 people participating in the workshop, and the confidence increased in a lot of different aspects, assessing, managing, preventing. So they did a paired t-test to compare the results before and after. So when the assumptions are broken, meaning the data is not normally distributed and the variance is very high, then the other opportunity to do the test for dependent t-test is the Mann-Whitney test. Independent test is the Wilcoxon signed rank test. The other way of managing the problem, you can also remove some of the outliers in your data. And of course, that is not always the best way to do it, because it depends on your sample size. Yes, if you have 5,000 people in your sample size, removing some people in your database may not be a big deal. But if you only have about 20 people, you don't want to remove any data point. So what if you have more than 2 means? You want to compare 3 means or more than 3 means or 3 groups of people. Then we use something called the analyses of variance. So that allow us to compare several means in this case. Instead of doing a t-test with the Anova analysis of variance, we do something called the f-test. So the question often people ask is, okay, so if you have 3 groups, I can do very, very similar things with t-tests. I can compare 1 and 2. I can compare 1 and 3 doing a t-test. I can compare 2 and 3 doing a t-test. So in other words, why do an Anova when you can run 3 t-tests, right, to compare the differences? Well, the problem is by running more tests, you increase the chances for creating error. That's why in statistics, we frown upon doing too many tests. Doing too many tests is not a good thing in statistics. So you're not trying to impress anyone by doing more tests. So in fact, the less tests you can use, the less tests you can prove your point, the better, because you reduce the amount of error and the chances of introducing that. So the concept of the f-test is very, very simple. You basically calculate the variances, and that's why it's called the analyses of variance. So the variance occur in 2 places. One is in the red, is between groups. So you have the 3 different groups in green, blue, and pink. So there will be differences in red, in the red arrow, indicating how much difference there is between the groups. But at the same time, there's also variance inside each individual group as well. Some may be larger, some may be smaller, right? So that's why you have the blue color. So the f-test to calculate the f ratio is by estimating all the variance in red over all the variances in blue color, the between group difference and the within group difference. That will give you the f ratio, and then looking at the number, you go to the f table to see if the level is significant. Of course, nowadays with computers able to do that for us. But at the end of the Anova test, the Anova test only tells you that there is a significant difference among all the groups, but you don't know where the group differences are. You still have to go back to do some post hoc tests individually. And the difference is, instead of at the beginning doing all the individual pair tests, you do your overall test first, and then you come back to do your pair test. So there are different options. In fact, for SPSS, for the statistical package for social sciences, has 18 different types of post hoc tests available for us. And the most common, the safe option is something called the Bonferroni. Basically, you control for the number of tests that you use in terms of the pairwise test. So the more variables you have or more groups you have in your Anova, the more comparison. So you control the significant level by factoring in the number of pairwise tests. There are other type of tests that they're less popular, like the toolkit test or Games Howell test. And just to give you another example, this is a study done recently as well. They look at the effect of interface pressure and skin surface temperature on pressure injury incidents and a turning schedule pilot study. I think it was done in Turkey. So what they did was have patients positioned at 3 different schedules and 3 different turning schedules, every 2 hours, every 3 hours, and every 4 hours. So you have 3 different groups, the 2-hour group, 3-hour group, and 4-hour group. And they recruited 444 individuals in the study. And when you have 4 groups, you want to compare the number of pressure injuries in the as your dependent variable. Then you can use a one-way ANOVA test. And basically, what they were able to find is that there's no difference in the occurrence of pressure injuries across the 3 different groups. So as you can see, there is no difference in interface pressure among the 3 different groups turning schedule within the 2 weeks of observation. So give you another example. This is a randomized control trial of using a photographic display with and without music on the operation-related anxiety. So, and of course, then you have the few different groups. You have the photographic display with music, photographic display without music, and also you have the music group. So then you can use the one-way ANOVA to see if there's a difference across different groups in the operation-related anxiety levels. In addition to a one-way ANOVA, there's also something called a two-way or two-factor ANOVA as well. And that's a little more complicated, and the sample size required to run this test would be a little bigger as well. Just to give you an example. So this is the outcome. So let's say what we want to see is people who failed a test, students who failed a test, people who were successful with the test, who did well, pass a test. So people may, and the hypothesis is whether they pass or fail the test has a lot to do with whether they blame themselves for passing, or they attribute themselves to the success of passing the test. So in other words, do they think themselves have a role to play whether they pass or fail the test, right? So that's the attribution of self. That's a concept. But at the same time, another variable may influence this relationship is the self-esteem level. So people, whether they have high self-esteem or low self-esteem, may affect whether they think the person themselves have a lot to do with the test outcome. You see how sort of intricate and complicated it could be by introducing the variable. So what you can see in this slide is, so let's look at here, success, they pass the test. People with low self-esteem, if they pass the test, they're less likely to think this is because of their ability themselves, compared to people who have a high self-esteem. If they pass the test, they're more likely to think it is because they are smarter. They themselves have the ability. But this relationship switch for if the test outcome is a fail. So individuals who have a high self-esteem in blue color, if they fail the test, they're less likely to blame themselves, to think it is their fault. Versus for individuals with very low self-esteem, if they fail the test, they're more likely to blame themselves for it. So this is a nice way, if you have a relationship and a intervening variable or a variable that can influence the relationship. In this case, the self-esteem may influence the relationship between the outcome of a test and the attribution to self, to think about the abilities themselves. So if you have this kind of hypothesis or this kind of study, a two-way ANOVA, it's very helpful to determine the actual relationship. And in fact, this is a nice picture to show you that when the relationship change direction depends on the outcome, success or fail, you can see that there's a cross there, the changing direction. We call that interaction. And it's a very nice way to show that there's an interaction between self-esteem and attribution to self. That interaction can affect the way that they see outcome, whether it's their fail or success. So I'll give you another good example just to illustrate this very complex study design. Let's say we have individuals with depression and no depression, and we want to treat them. We want to treat them with a computerized program. We want to treat them with using exercise. We want to treat them with meditation. And we want to treat their depression with social interaction. So as you can see, there are depressed and no depressed, and there are 4 different groups. And the 4 different groups would have different means and the different way to respond to the treatment. And people who are depressed, they seem to do better. They seem to do better with exercise, versus people who have no depression, they seem to do better with the computer. So then you have the group means and the grand means, and you can do the comparison. So to give you an actual sort of published example, this is a study by Mukai, and they looked at the effects of skin moisturizer on skin barrier function on the heel. And the heel was, they have the tape removal a few times and doing the study to determine if the moisturizer was able to prevent skin stripping or damage the skin. So the outcome, what they want to evaluate is the transepidermal water loss, or TEWL, and looking at the skin pH and also the hydration status. So those are continuous variables. So now you have the 3 different groups of people. The 3 different groups of people using moisturizer, people using emollient, and people using overcoat. And I didn't look at the study carefully enough, so I don't know what the differences they have for the moisturizer versus emollient. So probably something has a little more oil in it as emollient, versus overcoat, maybe something more acrylic related that you can spray on the heel. So anyway, so there are 3 groups: moisturizer, emollient, and overcoat. So yes, you can compare the means of, let's say, the transepidermal water loss level among the 3 different groups. So that will be a one-way ANOVA, right? But at the same time, I want to factor in the time factor too, because what they did in the study was they evaluated the response 5 minutes after the removal of tape, and also they evaluated with the repeat removal of the tape on day 7. So then now you have 2 different factors. One is the treatment factor, the moisturizer, emollient, and overcoat. The second factor is a time factor, whether it is the immediate or 7 days after application of the emollient and moisturizer, and the impact on transepidermal water loss as a continuous dependent variable. So that's why they have to use a 2-way ANOVA to analyze the data, because you have 2 different factors now. So in other words, we want to check on the, again, the assumption should be met, normal distribution, and it's important to check the interaction effect to see if those factors, in this case, if there were any interaction between the moisturizer, the last example that I was reviewing with you, whether there was an interaction between the moisturizer type and also the time factor. And then also the main effect, individual group effect or the time effect. The other type ANOVA is called repeated measure ANOVA. As the name implies, you can, so the only factor that you have is not about 3 different groups, but 3 different times. So this is a study that Professor Vera and her student had done, looking at the use of polyhexanide versus metronidazole for odor control. That was published in the JWCN journal as well. And they measure the odor over time on baseline, day 4, day 8. And then there's an odor score that people give. And then you can actually do a repeated measure ANOVA because now you have the 2 times. And instead of doing the t-score comparing before and after with the more than 2 time measurement, you can do what we call the repeated measure ANOVA. So quickly about correlation, I'm sure a lot of people have done correlational analyses already. Basically, if you look at all those scatter plots and identifying the strength of the relationship between X and Y, and the Pearson correlation coefficient R usually is, well, not usually, has to be either within the range of -1 to +1. A lot of my work in the past focused on the relationship between pain and anxiety. So in this case, there's a positive relationship between pain. As pain increases, also anxiety score will increase, indicating a positive correlation. More recently, there's a study that we have published in JWCN. We use a iPhone type device with a dermoscope to take pictures of the skin, so we can have a dermoscopic picture, and that will allow us for some evaluation to determine the quality of skin that we consider to be at risk for breakdown. So we use the term skin failure to describe the type of skin. So we come up with a few metrics, a few parameters, looking at the skin tone, the color on the picture, the opacity, is it transparent or is it opaque, scaling and scale, any cracks, and does it look firm, hydration status. So we actually see that skin frailty was correlated quite highly with number of those parameters, with strongest with the subjective evaluation of dry skin and the presence of scale. And of course, if the data is not normal, then you use the Spearman to evaluate your correlation. What about regression? Regression also is a very important statistical analysis, getting more and more popular. And in addition to correlation, we can estimate whether one variable is predictive of the other, one influence the other. So following the roadmap, the steps before you do any regression analyses, you look at the histograms, look at your descriptive statistics to make sure they're all normal, inspect the scatter plots to make sure there's no outliers, and the distribution is quite linear, because regression analysis is based on a linear line concept. And you also want to do a correlation matrix to see if actually some of the variables that you intend to use in your regression or multivariate analyses make sense. Because if there's no correlation, there's no point of putting them into your regression analyses, really. And then you can go ahead to do your regression analyses. So basically, your linear regression analyses is by plotting or estimating mathematically, using statistics, creating a formula of line to describe the distribution of your data. So yes, you can move it up and down and by changing the coefficient, the intercept point, and the slope, you can make sure that the line is the best fit. And that's why in statistics, I always look at the goodness of fit in terms of how good is your model, the line that you use to describe the data, fit with the data presented to you. And then the least square regression equation, as you can see, the least square regression equation is described here: y equals mx plus b, or y equals a plus bx. Depends on the country. You may have different ways of describing the linear formula. But at the end of your analyses, what we're curious about is two numbers, r and r squared. R is basically the correlation coefficient of the variables between the predictors and your outcome variable. And the r squared, what we can estimate is the proportion of variance in the outcome variable that is accounted for by all the multivariate variables in your model or individually. So it's helpful to look at, let's say you have 5 variables to predict pain scores. And of course, all those variables should be pretty much continuous. And you want to see if those 5 variables that you use for your model actually predict at least 7% or 8% of the variance in pain. Because if it only predicts 20%, then those variables you have used in your as your predictors, they're not that great because it's only predict 20% of the time. So you want to make sure that variables you use actually able to have a very good, have a very influential and can influence the variance in a significant amount. And there are different ways of when you're talking about the multivariate analyses, because the multiple variables, you can do hierarchical entry method, force enter everything simultaneously, or you can ask a computer to do a stepwise comparison or stepwise entering. And they're slightly different. I think usually it depends on your theory and your hypothesis, and also depends on the existing literature, whether one variable you think is stronger than the other that should be entered stepwise first, versus that you don't really know the true relationship, then you can enter them simultaneously using the forced entry method. Again, some of the work that I've done before, looking at psychological attachment, anxiety, and how they influence pain. And we use number scale for pain. We use another relationship scale for attachment, psychological attachment. And we also look at the anxiety using Spielberger's trait anxiety inventory. So yes, we can estimate the relationship. So as you can see, the beta and the amount of variance. So attachment account for 21.3% of variance in anxiety, and it also attachment affect 13.7% of pain. And the beta basically identify the strength of the relationship, if you may, is about 0.44 versus the relationship between attachment and pain is 0.227. So what I did was, and I also regress using a regression analysis to look at the relationship between pain and anxiety. As you can see, the beta is pretty good. So, and then I enter anxiety and attachment at the same time. As you can see, now the relationship between attachment and pain had dropped down by entering anxiety in the same equation. So that's why whether you enter the variables simultaneously or individually has a big role to play, whether that's going to influence the relationship. In fact, this is what we call this type of analysis is what we call a mediating analysis to check for the mediating effect. Within this case, the anxiety is a mediator in the relationship between attachment and pain. Probably closer to the end, I want to talk about the logistic regression. This type of regression is different from the linear regression because the linear regression, the outcome variable has to be continuous, versus logistic regression. The typical logistic regression is a dichotomized variable. There's also some other multimodal and Poisson logistic regression. For the interest of time, so I'll focus on the logistic regression, the traditional logistic regression with outcome has usually have two possibilities, whether, for example, the mortality, dead or alive, quality of life, high or low, mood, happy or sad, and response to treatment and wounds, open or closed, healed or not healed, basically. So this is a study done again with your group, with Professor Vera, and looking at exploring the risk factors among individuals with diabetes and amputation, and they were able to recruit 114 individuals, and looking at the relationship between amputation and Charcot neuropathy. And in this case, the outcome variable, yes or no, is your Charcot neuropathy. And the number of variables to see if there's any predictors associated with Charcot-Foot neuropathy. And the only variable that has a strong relationship was the BMI, the body mass index level. As you can see, the odds ratio was 1.08, 95% confidence interval was 1.001 to 1.743. So you can see why it's important to report your 95% confidence interval. So the logistic regression, the important thing is for us to be able to calculate the odds ratio. And that's why it's so popular in epidemiological studies. To interpret the odds ratio, if the odds ratio equals 1, because it's a ratio, right? So the chances of happening is 10, chances of not happening is 10, so it's 1. Then it's equal. Then there's no association at all. The odds ratio is non-significant. Versus if the odds ratio is more than 1, then it means that the exposure, there's a positive association, versus the odds ratio less than 1, there's a negative association. In the logistic regression, it's also very important to look at not just the odds ratio, but looking at the 95% confidence interval, because to be confident, you have to make sure the interval doesn't include 1. Because whenever the 95% confidence of intervals for odds ratio that includes 1, meaning that there's always a chance that this is just a fluke, this is by chance is happening, you cannot trust the data that much. There are other type of ratios that you see in epidemiology studies. People may calculate the relative risk, odds ratio we just talked about, or the hazard ratio. And they are very, very similar, but using different types of tests. Logistic regression for the odds ratio. We may use something called the Poisson regression for odds ratio, and the hazard ratio using survival analyses. And then going to some of the non-parametric tests. A lot of you may be familiar with chi-square tests. basically when you have two categories of the predictors or the independent variable, and then two categorical outcome for your dependent variable. So that will be a chi-square test. For example, fecal exposure, no fecal exposure, whether people develop infection or no infection. So I want to show you the other type of analyses, what we call a survival analysis. It's often done in wound care literature. I think I should say helpful if you're tracking for wound healing over time. And this is a study that was done by Dr. Kim LeBlanc and myself, looking at evaluating the use of silicone type material for the treatment of skin tears compared to non-silicone based product. And the duration of the study was 3 weeks because we believe most skin tears should be able to achieve wound healing by 3 weeks. So those are the products we use. In the treatment group, we use silicone-based product. In the control group, not silicone-based product. And we measure the wound size. We measure the healing rate per day. We took photographs. We look at the outcomes. And in order to evaluate skin tears or to describe skin tears, we use the ISTAP classification system that Professor Vera is the member of. And so the type 1, type 2, and type 3. And you can see the outcome. We got 126 people participated in the study. There are different locations, most likely in the extremities and arms and legs. And there are different variety of skin tears, mostly the type 2 and 3. The important part is we're able to describe in this graph the proportion of people achieve complete closure of the skin tears, divided into two different colors: the treatment group and the control group, the silicone in blue, and then the control group in red. And you can see that there is a high number of people achieve complete closure in the silicone group consistently in week 1, week 2, and week 3. So yes, graphically it looks great. So what else can we do? So we actually did something called the Kaplan-Meier survival analyses, and to determine if those week by week differences were significantly different. So as you can see that the estimated day for complete closure in the control group was 21.7 versus the control group is 11.06. And because we had multiple time points, so it's more than just doing a chi-square test and taking in all the information with the survival analyses, we're able to identify the chi-square analysis was a significant finding. And you can see 95% confidence interval. They were quite tight, so it's a very trustworthy number. And often in those survival analyses, the graphs are very important as a point to illustrate the differences. As you can see, survival meaning that how long in this case, how long do people not survive skin tears, but how long was the skin tear exists? And so as you can see in the silicone group in red color, the number of people drop off quite quickly at each time point, versus people in the blue color in the control group, the drop off is more. There's a big difference between the two curved space that you notice there in terms of the number of days and time at each time point. So, and that's basically a quick review, if you may, of some of the tests that we use. And look, I'm getting quite dark already. Time flies when we talk about statistics.
Thank you very much, Professor Kevin. I think that you gave a big panorama about statistics, but in a very didactic way, very simple way. I think that it will be very helpful for all students who are participating in this open lecture, this colloquium. I give the word, or Adriane, Raissa. It's the questions the questions are with you.
Thank you, Professor Vera. Thank you for your presentation, Professor Kevin. We have many participants in this seminar, graduate students and professors from higher education. Professor Monica is participating here too. We all have the participation of the Brazilian Central Theorem. And some questions here in the chat. We'll ask the first question. Why is Statistical not to use?
Raissa, Raissa, I think that your internet's not good.
Mm-hmm. It's breaking all the time, interrupting all the time, Raissa.
Excuse me. Adri, I can send to you the questions.
Okay, I have the questions here. I can talk. The first one, it's how to analyze statistical results without forgetting about the clinical importance of data.
Yeah, that's a very excellent point. And I think that's why in your conclusion, in your discussion, you should always comment on the clinical significance of your finding. Because if you have a very big sample size, you can always find something significant. It's by chance, right? Probability. The more samples you have, the more people you survey, the more likely you're going to find something. So actually, I was just looking at a study that that the value, I think it was a Carroll study, the health quality of life, and the numbers were so close that there was a significant finding, a significant difference. So it's just by chance, either by chance or because the sample size was so big. So then in your discussion, and sometimes reviewers may give you some trouble by saying, well, the difference between 30 and 29 is not that big in terms of quality of life. So it's not something that we should be excited about. So as long as I think you acknowledge that and acknowledge that that this is a big sample size, or there may be an error, and may not be clinically significant.
Okay, thank you. We have one more question, and Raissa is going to tell you, but I have the question here. It's why it's becoming common not to use the p-value in some studies, and it is the limit for the 95% in CI, for example.
Yeah, I think less and less people, when you submit your paper for reviewers, they don't always trust your p-values. Because as I mentioned before, the p-values, if you have a big sample size, you can find a p-values quite easily that is less than 0.05. And that's why when you describe the range, the 95% confidence interval, it gives the reader a better insight how spread out your data is. Because if you're 95% confidence interval for age, as I mentioned, is from 15 to 95, even though your p-value is less than 0.05, I'm not quite sure I can trust your mean value that easily. So I think it's valuable to make sure that you have both in your study, and some journal even just ask for confidence interval, not the p-value.
Okay, thank you. And now talking about the big data, we have one question about the advantage and the disadvantage of the big data.
Well, the advantage is it's very generalizable. The bigger the sample size, the more generalizable it is. And if you have big data, and I presume the question is about a database, right? So there's a lot of databases in Brazil and also in Canada as well, that if you have access to the government, access to some health authorities, they collect lots of data. So the problem with those data sets is you may not be able to correct them. And there's maybe some missing, some error in terms of how the data is being entered. But the advantage is collecting data is very, very time consuming. If I have to collect 5,000 surveys, it would take me 5 years to collect that. And if you're doing a PhD, you don't have 5 years. You have 1 year, right? So that's why it's important to recognize that there are benefits and advantages and disadvantages. I do a lot of big data analyses as well. And that's why you want to make sure you use a trustworthy database, and also to make sure that there's the way to validate the database.
Hi, sir. We have one question, so I have the last one. You want to talk?
Yeah. Can you hear me?
Yeah, it's better now.
It's better. So the other question is about big data. We were example with 20, 30, 50 variables or more. Does this number of variables put descriptive studies, case, ecological, cross-sectional, cohort, on a new level, or do they keep the same limitations?
I think people are often shy about talking about limitations of the study. It's not about exposing your weakness. I think people should be very liberal to talk about limitations. There's no perfect studies, and every study has limitation. I think it's just about being honest and being critical about your own work as well. It is a very scholarly attitude to be able to criticize your own work. I'm always standing in front of people and say, well, my studies is not that great because it's small sample size, it's not randomized, there's a lot of bias, and so on and so forth. But I think it's part of what we learned, and try to be very upfront and very honest about the study.
Dr. Kevin, you said that we used to collect a lot of data. And think about that. You have any advice about publishing and these data analysis?
Yeah, I think when you have the data, you can generate a number of research questions based on the data. I think some of the theses that I participated at University of Sao Paulo, I think one of Vera's students look at lake ulcers and looking at predictors, foot ulcers. I think one study I showed you earlier too, the Charcot neuropathy. So yes, I think it's looking at the database is very valuable. It's always challenging to determine what's the best question to ask. you don't want to be fishing just to do exercise. You want to make sure that whatever question you have is meaningful, is original, it is significant to make a contribution to how we understand wound care or the ulcers or diabetic foot ulcers, not just any numbers and put them together and do analyses.
Thank you so much, Dr. Kevin. These are the questions that we have in chat. I don't know if Raissa is gonna tell something and you are ready to finish.
May I complete something, Adriani, about the limitations of the studies? I think that it is also important to point out the strengths of the study, because sometimes you start your discussion saying that or writing that the study has many limitations, etc. No, we must focus firstly on the strengths of the study. As Professor Kevin said, it's important to point and to reinforce what we have learned about this, what we not just learned, but the contribution for clinical practice. I think that this is important. So to show what is the strengths of our studies. Thank you.
Yeah, that's an excellent point. You can start with saying this is the first study to evaluate it. This is one of the few studies, and then sort of highlight some of the key strengths. Yeah, that's an excellent point. Thank you.
Excuse me, just a minute. Professor Kevin, once again, we would like to thank you for your participation and the willingness to contribute to us. And I pass the word to you and for Professor Vera. Do you have any final comments? And that is,
No, Raissa is not okay again. No.
Adri,
I just would like to
pass the word to professors and finish, please. Thank you. Excuse me
yes.
because it's a bad internet today. I don't know why.
Professor Kevin, your final comments or your final message to this for today, please.
Sure. I think thank you so much for joining us this evening. It's always great to have this dialogue about, in this case, statistics. I hope you've learned a few things or have a chance to review and refresh some of the key concepts in statistics. It's not an easy topic to talk about. It's not an easy topic to listen to. So I appreciate your patience and your interest, sticking around for such a long time. Look forward to meeting you again and in the near future. Thank you so much for the opportunity.
Thank you, Dr. Kevin. We thank you for the opportunity and Professor Vera for being with us tonight. Thank you so much.
Thank you all. Thank you for your partnership with us, with our research group. Thank you for all the students who participated in this session. I'm sure that you learned a lot. You remember something and remember something and learn a lot. Thank you very much. Thank you very much.
Thank you and good night for all.
Have a good evening. Thank you.
For you all. Bye-bye.
Bye-bye.
Ai, o pessoal